So another way to prove some statement, so an equality or an identity, it's actually to use a proof by equivalence. So I'm going to somehow show you two different ways, which at the end they are a bit the same. But the first one, it's taking the left-hand side, A, and turning it into another statement, which is C, let's say. And then to take the right-hand side separately, and then making some logic argument, turning that into the same statement, okay? It means that in this way we have proven that A and B are the same because they are equivalent to something that is C, and C it's the same. In the second method, instead, you take A equal B, and you really transform the whole statement, and you claim that this is equivalent to another statement. So this is the symbol of equivalent. And you turn it into another equivalent statement, and so on, since something it's coming out that looks like something that is true. For instance, it could be typically it's something that looks like either 0 equals 0 or 1 equal 1 or something like that. So let's try to have an example for the first one. Let's say that I want to prove the identity of 2a plus b squared minus 4a squared minus b squared, identity a plus b all squared minus a minus b squared. So you see here, it's actually more convenient to work independently each side and reach a common statement C that then we compare, right? So we take the left-hand side, and the left-hand side is going to be equal to 4a squared plus 4ab plus b squared minus 4a squared minus b squared. This gives me 4ab, because you see this one cancel this one, and this element cancel this one, so we are just left with the common product, while the right hand side is going to be equal to a squared plus 2ab plus b squared from the first term minus, and then I can open the parentheses, a squared minus 2ab plus b squared. And then again, here, a squared cancel out with this one, b squared cancel out with this b squared, and what I'm left, it's actually 4ab again. So I have proven, okay, that the right-hand side, it's actually equal to the left-hand side using the equivalence to another statement that it's the same for left-hand side and right-hand side. Now, the third method to something true, for example, can be seen in this example. So I have an identity that says that a minus 2b is divided by a minus b, and this is equivalent to a squared minus ab minus 2b squared divided by a squared minus b squared. And you see now, this expression is quite hard to go from the left-hand side to the right-hand side. Maybe we could here from the right-hand side to the left-hand side, but somehow maybe it's more useful if we work out algebraically these fractions. And one way is to multiply out this numerator on the left-hand side by the denominator, right? And multiply a minus b by this term here. So actually, this means that I can write down an equivalent statement which tells me that a minus 2b times a squared minus b squared, it's equal to, and then I have to use correctly parentheses, right? A squared minus ab minus 2b squared times a minus b. And now I have to work out the left-hand side and the right-hand side. So I'm going to have a cubed minus ab squared minus 2a squared b plus 2b cubed equal to, now I'm working out the right-hand side, so I'm going to have a cubed minus a squared b minus a squared b plus ab squared, and then I will have minus 2ab squared and plus 2b cubed. And now you see here that on the left-hand side I have this term, but I also have it on the right-hand side. I have a cubed, I have also here a cubed, And now here I have to rewrite actually this statement into a more sensible thing that I can actually work out. So let me understand here, what do I have? I have left this one equal to, now here I have minus a squared b minus a squared b, so it's minus 2a squared b, and then I have ab squared and minus 2ab squared, that makes it minus ab squared. All right, so I can really see that here I have minus ab squared, and then I have minus 2a squared b minus 2a squared b, okay? So what I'm left with, it's actually an equivalent statement that it's 0 equals 0. And that's my demonstration.